Very likely, in many of those years, his citations equaled the sum of the rest of our citations. They were typically in the hundreds per year, and for a mathematician, that's quite a lot. So we became an internationally recognized department, largely due to Jack's influence and the existence of the Center for Dynamical Systems and Nonlinear Studies. And that was great. It was a great success. But that's not the best part of bringing Jack Hale here to Georgia Tech. The best part was Jack as a person. It was a true privilege to become a friend of this completely unassuming man who always had this humble accent of Eastern Kentucky and always had a tremendous amount of generosity and warmth to everyone, from students up to international scholars. If you could talk mathematics, you were on a direct line of communication with Jack, no matter whether you were well known or a nobody, what part of the world you came from. It was just a glorious experience. So his influence on his area of mathematics was vast, as I think everybody in this room knows. But it was a soft influence. It was the influence of a teacher, an explainer, and a visionary who had an infectious way of engaging mathematics. In his hands, dynamical systems was really not a discipline. It was more an entire philosophy of mathematics and science. So please enjoy this meeting, learn a lot. If he were here, Jack would certainly be looking forward to the lectures, the contacts with old friends, and the opportunity to meet the younger generation in dynamics and differential equations. And I also hope that while you're here, you'll look at our campus and savor the sunshine and perhaps more flowers than some of the places you come from, looking at Minnesotans. You might even have the opportunity of experiencing a pollen level that exceeds anything else in your prior life. It's one of the joys of Atlanta at this time of year. But mostly, please celebrate Jack's legacy and influence, and remember him as a person. And also, I know many of you also knew Hazel, and I'm sure you'll have some thoughts for her as well. Thank you. Oh, yeah, the microphone.
I'm Doug Ulmer. I'm the chair of the School of Mathematics, and I'd like to add my welcome to you for this conference in honor of Jack Hale. We're very happy that such a distinguished group has come to Tech to help us celebrate his work and his legacy. I understand that there are over 250 participants in the conference and over 100 speakers, including many of the leaders in the field, and of course many students, friends, and former colleagues of Jack. So it's a fitting tribute to a great man and a great career. Evans has already done a very good job of doing the biography of Jack, so I'll skip most of that. I want to tell you a few other things about him, in particular some of the awards that he received. And are far too numerous to list all of them, but I would like to mention that he won the Chauvenet Prize for Exposition in 1965. He was a speaker at the International Congress in 1966, and a Guggenheim Fellowship in 1979, and he won the Georgia Tech Sigma Psi Sustained Research Award in 1991. Again, too many to list, but Jack received many honorary degrees and was a fellow of many societies, including the Brazilian Academy, the Royal Society of Edinburgh, and the Polish Academy of Sciences. He was a distinguished visiting professor at several very interesting places, including the Lorenz Center, the Newton Institute, and the Japanese Society for the Promotion of Science. I checked on MathSciNet. I like to use that. Evans likes some other sources like Google search, but I like the conservative, rock-solid database of MathSciNet, and it lists over 250 papers by Jack and an astounding 6,825 citations last night. I'm sure it's even larger today. Several of Jack's books are classics and standard reference in the field. And very importantly, Jack supervised 43 PhD students and has over 125 mathematical descendants in the genealogy project. I know many of those people are here, and we're extremely happy to have you here to celebrate Jack's life. Jack's influence here at Georgia Tech was very profound. As Evans mentioned, during the 70s, during the Institute presidency of Joseph Pettit, from 72 to 86, there was a dramatic increase in emphasis on research, obtaining federal grants, and improving the quality of the faculty. At that time, barely half of them had PhDs, and of course there was a great desire to change that. There was a bit of a rough patch in the early 80s due to budgetary and economic developments, and then the presidency of John Pressine continued in this direction. Jack's appointment in 1988 was really a watershed moment for the School of Mathematics. Under his influence, the quality and reputation of the school increased dramatically, and we'd like to think that trajectory is continuing to this day. Now, I never had the pleasure of meeting Jack, unfortunately. I came here long after he was gone, but he, I'm told, had a very generous and inclusive working style with many collaborators from around the world and a lifelong interest in mentoring and developing young talent. Because of this, we can't think of a more fitting tribute to him than positions in his honor that support young people. And I'm very happy to tell you that the School of Mathematics has inaugurated a new postdoctoral program called the Jack Hale Postdoctoral Fellowship. We'll be welcoming 5 fresh PhDs here in the fall to take up this position, and we hope that this program will grow quite a bit larger than that in the end. That's the plan, and that will become a permanent part of the mathematical landscape here at Georgia Tech. So please send us your best and brightest for these positions. This will be an annual recruiting campaign. Now, I know you're all anxious to get past the speeches and on to the mathematics, so let me close by thanking you once again for coming to Georgia Tech and contributing to this conference in honor of Jack Hale. I'm sure you'd be delighted to see many old friends and distinguished colleagues and hear about all the interesting mathematics that's taking place in this area. So I wish you a pleasant, productive week, and welcome to Atlanta and to Georgia Tech.
Okay, thanks, Doug, and also Evans. I think we are about it's time to start the regular program. For the conference, we create honor lecture series is called Hale Memorial Lecture, and we hope this will be a tradition for the following conferences. Let me pass the microphone to George, who will introduce the speaker. And meanwhile, we have the screen, everything set it up. And Raphael, you have something to add?
No, I was telling you to put the microphone on the laptop.
Oh, why is that? It is too late for that.
Together with Joe Bowling, which appeared in 1988 in the Mathematics of Computation journal. Probably it's the only paper that Jack published in a basic. And okay, I will speak more about mathematics, but also I will tell you some more stories maybe tomorrow. And what I would like to say, so I was not a student, as you just realized, of Jack. And nevertheless, I would say in German, when you speak about advisor, you don't say advisor, you say Dr. Vater. This means Dr. Father. So, and I would like to say that Jack was like a father for me in mathematics. Jack was very generous with his time, not only with me, but also with all his students. And what I would like to add before speaking about mathematics is that he had a clear vision of a lot of problems in dynamical systems. So sometimes he told me, I knew nothing in dynamics. So he had to teach me something, but he did not teach it like a teacher, but he told me about dynamics like he would tell a fairy tale, I would say. So it was very nice. Okay, sometimes he neglected a little the technicalities, but I was here, I was there to remember him that there was some technicalities, and then sometimes he was a little nervous because I was reminding him too much the technicalities. But it is all what I want to say now, and so I put some. I put some pictures. You will have some more tomorrow. So at the beginning, so this is a picture in the Callaway Gardens, made, I think, in April 1991. So it was the same, you see, it's the same season with the nice dogwoods. And if I speak about Jack and if I think about Jack, now I cannot think about Jack without thinking about Hazel. So the next picture is a picture of Hazel and Jack in Fontenay on our balcony. So, and at the end of the talk, when you will be very tired, I will show you a few other pictures. So let me go to the talk. And I will speak about Kupka-Smell and Morse-Smell systems and about stability. For several reasons, it's an important question in dynamical systems. So if you have a family of dynamical systems depending on the parameter lambda, and you know something about S lambda 0 of t, it means when lambda is equal to lambda 0, can you say something about the dynamics of S lambda of t? So usually it's very difficult. So Raphael Delalave in his lecture yesterday addressed the same question, but he, after that, told that he would give concrete examples. Unfortunately, I cannot give really concrete examples, so I will more speak about generic examples. So anyway, what I want to say is that when you look at a dynamical system depending on the parameter lambda, you want to know if you have stability. So you have two kinds of stability. You have what is called local stability. Local stability. It means if you have equilibria, will you still have an equilibrium nearby when lambda 0 is replaced by lambda? Will you have still, if you have a periodic orbit, will you still have a periodic orbit? And global stability or structural stability, it means that you have the same dynamics. I will explain later what it means. So, but these two properties, or local stability or global stability, are related to hyperbolicity and transversality. So hyperbolicity is very important to have at least local stability, and transversality will give you something that I would call a semi-local stability. So now, so you can ask the following question. Do we have hyperbolicity? How can we describe, or do we have systems where we have hyperbolicity of the critical elements? So I remind you that critical elements, it's a set of periodic orbits and also of equilibria. And so one question is can the hyperbolicity be generic? The same question is, do we have systems where you have transversality of stable and unstable manifolds of the critical element? And you can also wonder if this transversality is something generic. So if you have hyperbolicity of the critical element and transversality of the stable and unstable manifolds of the critical element, you will say that your system is Kupka-Smell. So don't forget that till the end of the talk, what means Kupka-Smell. And if you have Kupka-Smell, and if you know something more, say for instance, if you know that the non-wandering set is a finite number of critical elements, then you call the system Morse-Mail. So you can ask, when is the non-wandering set a finite number of critical elements? This is far from, it's very rare in some sense, but we will have some examples. And if you have a system which is Kupkas-Mail, I would tell you that this gives you local stability or semi-local stability. And if you have a system S lambda 0, which is Morse-Mail, you will have structural stability when you have some perturbations which are regular enough. So my talk, the first talk, I don't know if I can go till the end because it's a little long, but I have a second lecture tomorrow. But the first part of the lecture is some kind of review, some panorama about some main theorems, main results in infinite dimensions. And in the second part of the talk, of the lectures, I will give some proofs, or rather some ideas of proofs, because the proofs are rather technical and somehow delicate. So the second motivation for giving this talk is that Jack Hale was very interested in local stability, structural stability, Morse-Mail systems. And he had a big influence on these questions in infinite dimensions. So I would like to remind you that Dan Henry was one of his students, and Dan Henry had the first beautiful result about transversality of stable and unstable manifold for a parabolic equation in one dimension. And also, personally, Jack Hale, he told me about structural stability, Morse-Mail, and so on, very early, I think in the 1988, 1989. He was teaching me about such question, and I remember that maybe 1987, he told me to read, there was this paper, the first paper of Oliva, Valdir Oliva, who proved the structural stability in infinite dimension. But I will come back later to that. And so to illustrate that, I would like to show you, so in 1989, I spent 1 month in Georgia Tech, and Jack Hale was speaking with me about, he told me, like usually, about a lot of results, and here, he was speaking about the paper that he had written with Lin about perturbation of heteroclinic orbits for DD equations. And I remember that he was speaking about that. And maybe he was thinking, but he did it, he translated it in the language of ordinary differential equations, like you can see. Like you can see it here, x dot equal to f of x, and he say, assume that you have a heteroclinic orbit, gamma t, and so he introduced the linear variational problem, and he spoke here about exponential dichotomies. And this actually is a fax of May 1589, as you can see here, because I was there in April, and probably in late April or the beginning of May, he was thinking that his explanations were not clear enough, and he sent me this fax to make it clearer. So you have the second page, so it's a long fax, I don't want to show you the fax, and you see, so here he takes a perturbed equation, x dot equal to f of x and g of x, and then he looks at the linearized equation and see, so there is this classical lemma, no, it's classical about the range and the null space of this d by dt minus a of t operator. So you have the lemma, and okay, it goes on. He quotes Henry, page 128 in the lecture notes of mathematics. And so it goes on. So after having given the motivation, I want to give you two examples to illustrate what I mean by dynamical systems. So the first one is the basic a basic ODE in RD. Okay, I take it in RD. I don't consider it on a compact manifold of dimension D, what I could do, but I take it on RD because you will see later why. And so here you have no compactness because you look on the vector field in RD. So you impose, I just impose for the sake of simplicity, I impose that G, it has some dissipations. It means that for y, for the norm of y bigger than some constant m, I assume that the scalar product yg of y is strictly negative. So if you have that, of course, then this ordinary differential equation generates a global dynamical system. And because Jack was working a long time, it was a period of compact global attractors, and he introduced also this terminology. So, and remind you, okay, here is the case of RD of ODEs, it's very easy. So you have, with this condition, with this dissipation condition, you have the existence of a compact global attractor AG. So I read to be compact, invariant here, and AG will attract every bounded set of RD. So this is the first example, but I put it for historical reasons, like you will see later. And now I go to my favorite subject, which is PDEs. So I take, this is a parabolic PDE, du by dt equal to Laplace u of xt plus f of x, u of xt, gradient u of xt, where x belongs to a bounded domain, and for t positive. And so, since I have a bounded domain, I need to put a boundary condition. So I take the simplest one, which is homogeneous Dirichlet boundary conditions, and I take function space y, so that I have the existence of the things written in the correct way. So if you don't care about that, you just say, you just see the nonlinear semi-floor. And the same as in finite dimensions, you want to say, okay, in some cases, I have a global, I have only global existence, global solutions, and I have a compact global attractor in Y. So I put some condition. So this here you find again a dissipative conditions, okay, which looks like you had no, sorry, it's the other way. Okay, it looks like here, like these conditions that I have here. Okay, so this looks very close to that. And here I put a ground condition because of the presence of the gradient of u. And I took this condition in some paper of Peter Polacek, so, but it is probably not the best condition, but sorry, but it's some condition which gives you the global existence and the fact that you have a global attractor. But I don't care here about existence and uniqueness, so let me go further. So, for the people, so I did not do any tutorial yesterday, so I was just thinking that for the people who are not doing really dynamics, I should recall something. And since the whole talk, since in the whole talk I speak about hyperbolicity, I have at least to give to remind the definition of hyperbolicity. So, in the whole things about Puck-Casmel, Morsmel, and so on, what is important is are the linearized equations along connecting orbits or along periodic orbits or at about equilibrium point. So I just recall you. So if you take my favorite parabolic equations that I had, So you linearized around an equilibrium point, you get this is a linearized elliptic operator, you see, and you say that E, the equilibrium point, is hyperbolic if for any eigenvalue of this operator, the real part of lambda is not equal to 0. And I recall you that the terminology that the Morse index, M of E, is the number of unstable eigenvalues of LE. This means the number of eigenvalues with real part positive. So, okay, this is the simplest case of hyperbolicity. Now we go a little further. We take a periodic orbit. You take the linear operator defined by the linearized equation. Here I tell you that, of course, now it's a non-autonomous equation because P depends on T and X. And since I started with an autonomous equation, dP by dt will be a solution of this equation. So this means that if I look at the period map, P of omega 0, where omega is the period of P, I know immediately that the spectrum of the period map contains 1. So we say that gamma is hyperbolic if 1 is an isolated simple eigenvalue of the period map. And again, you can define the Morse index, which is the number of eigenvalues, such that the absolute value of mu is bigger than 1. And I recall that the equilibrium point and periodic orbits are the critical elements. Now, there is a second tutorial thing, but I will not read it. It's just to remind you what is a stable set and unstable set. And in the case that I am looking for a parabolic equation, because I am on a bounded domain. On the bounded domain, all my stable sets will be of finite codimensions, and all my unstable manifolds will be of finite dimension. And here I just recall you what it means to be, this is a sign to, this is a notation to tell what it means to, this is a notation W1 transverse to W2 at U0. So I just recall you the definition. So it is in finite dimension, you just put that, but in infinite dimension you have to say that T of U0, the tangent at U0 of W1, contains a closed complement of T U0 of W2. Okay, here it's some pictures. So you have the local stable manifold and the local unstable manifold and the picture of the flow. And here it's a global. You see here you have a homoclinic orbit with a stable and unstable manifold. Sorry. And here's the last tutorial thing, which is about what is the non-wandering set. You can read it. And of course, if you speak about genericity, you have to put you have to put some topology on your space of CR functions. So in the case of the parabolic general scalar parabolic equation, I have a function G or F, I called it F, which goes from which is CR from the closure of omega cross Rn, because omega is a bounded set in Rn, to R. And here is the topology, the Whitney topology. You could take some weaker topology, but if you take weaker topology, your result will be weaker. And for Whitney topology, I would, if you don't know well about it, you can look in the book of Hirsch or in the book of Golubitsky-Guillemin, where I learned about Whitney topology. And okay, so this is a bare space. It means that any countable intersection of open and dense sets, it ends in GR. So GR is my CR with the Whitney topology. And now let us go to some history. So I want first to recall what happened in in finite dimension before going to infinite dimension. So it's a quick history. So I think the first, as far as I know, the first real paper about structurally stable systems was a paper in 1937 of Andronov and Pondriagin, where they were speaking about system grossier, it means coarse systems. And after that, in 1959, around 1959, and it is in a paper in 1960 in the bulletin, in the bulletin of the Mathematical Society of Mexican Mathematical Society, Smell gave three conjectures. Okay, it was a little strange, but because he knew some work of Poincaré, so he was saying that more or less that the Morse-Smell systems are structurally stable. Okay, he did not call them Morse-Smell, but he gave what I just gave you before, this system which has this property. So he said that the Morse-Smell systems are dense, that they are structurally stable, and that every structurally stable system was of Morse-Smell. Okay, so of course you know that only one conjecture was correct, and so. But he immediately, maybe a few months later, remarked that it was not true, that there was no density of Morse-Smell systems. And in 1962, Peixoto proved the three conjectures when M2 is a compact orientable manifold of dimension 2. Later, I just go faster, in 1963, Smell, and in 1963, also Kupka showed the genericity of Kupka-Smell systems. So you have Smell gave it in a Chile course in 1962, and Kupka was a contribution à la théorie des champs génériques. Let me go a little further in this history. So in so after Smell, of course, he corrected everything, and in 1965 he gave other conjecture with the axiom A diffeomorphisms, but I don't want to speak about that because in the infinite dimensional case there are a lot of problems with Morse-Smell systems, and it's not so easy to work with axiom A diffeomorphism. Of course, somebody like Peter Polacek, he is able to construct everything with his realization theorems for parabolic equations. So you can surely construct systems which are axiom A and not Morse-Smell. So in 1967, I just want to quote this paper of differentiable dynamical systems of Smell, and Ruel told that it was a masterpiece of mathematical literature. And after that, in 1967, Peixoto gave a nice proof of genericity of Kupka-Smell. And now, nowadays, in infinite dimension, one uses the same kind of proof, the same way to prove it than as Peixoto. And then in 1969 and in 1970, Pallis and Smell proved the structural stability of Morse-Smell system for any compact manifold of dimension D. And I want to finish this summary, this historical summary, by pointing out that there is an interesting paper in 1979 of Robin, where he was looking for an algebraic Kupka-Smell theory. It means, in some sense, one part of the people who show transversality for in infinite dimension used functional formulation of transversality, which is a little more elaborate, but I think it's the same spirit. So to summarize, if you have in infinite dimension, if your dimension is 1, you have automatic transversality of stable and unstable manifolds. So this is very trivial. You agree with me? But I would like to make the parallel, which is the parallel with the parabolic equation. So the parallel with the parabolic equation will be the result, but which is far from being obvious. It will be the result of Dan Henry. When you look at a parabolic equation in one dimension, you have automatic transversality. So I want to make a parallel. So you see, you have this parallel, d equal to 1 for the vector field corresponds to n equal to 1, I mean one dimension on 0, 1 of a parabolic equation. Now let us go to d equal to 2. So you have your vector field in R2, and okay, it's on the plane. Everybody knows that you have the Poincaré Bendixson property, and if you have this, if you have some dissipation, you can say that you have generic Morse-Mel property, and this is stringing. This is the same if you take a parabolic equation not on 0, 1, but on S1. So you take my favorite parabolic equation, then you can have periodic orbits, and you have the Poincaré Bendixson property, which was proved by John Maleparé and Bernard Fiedler, and this helps you to go till the end to tell you that you have generically Morse-Mel. And okay, if you are on a vector field for d bigger than 2, you have just generically Kupka-Mel, unless you are in the case of gradient systems where you have generic Morse-Mel. And it is the same if you take a parabolic equation on a bounded domain in Rn for n bigger than 2. You will have only generically Kupka-Mel or generically Morse-Mel if you are gradient. So now I go, I still have, I think we began at which time? I have 25 minutes? Okay, so it's, you are sure, not 26? Okay. So now let us go now to the part 1. Now we are going seriously. We shift to infinite dimensions. And so the first thing that which is normal to do, and I was speaking about to you before, it is the result of Valdir-Oliva in 1982 that you find in the book of Hale, Magalhaes, and Oliva in 1984, which is the structural stability of Morse-Mel systems. So the proof, I mean, it's a proof in infinite dimension, but in this proof you don't see if you have an FDE or if you have a PDE. So what you do is just you have to adapt in some way. The difficulty is to find here, I think, the good hypothesis. Of course, you cannot expect. I think that you cannot expect to have structural stability of a conjugacy on your whole space, on your whole space Y. So you have, so Oliva introduced A of S. So if you have a map, a CR map from Y into Y, with R bigger or equal to 1, so what you do is you somehow you introduce the A of S, which in many cases is a global attractor, the compact global attractor, but here it's just the maximal set of the bounded trajectory of S when N belongs to Z, okay? And now you take any subspace of your CR maps from Y into Y, so that you have these properties. So first property, you need to have somewhere compactness. So you assume that A of S, you take a subspace so that for every S in this subspace, A of S is compact. And you need some injectivity properties. So Oliva called it not injective, he told it reversible. In PDEs, we would say backward uniqueness properties. And so he assumes that S restricted to AS is a C1 injective map. So it means C0 plus, and the same for the derivative. And you need to assume something about the AS when S varies. So he assumed he take a subset so that AS is upper semi-continuity with respect to S. Okay, if you take such a subset, then you can show that the Morse mail is open in this subset. And you have S stability. It means that you have structural stability. In other words, here you have a conjugation between AS and A sigma for sigma close to S, but restricted to this maximal invariant set. So this, and Valdir-Oliva, he proved it, so it's a generalization of the geometrical proof of Pallis and Smedge. Okay, you could do maybe, you could do other proofs which are more analytical. And Kenny Liu in 1994, he had another proof for parabolic equation where he has a conjugation in the neighborhood of the compact attractor. And in 2002, Oliva gave the proof for the flows and semi-flows. So I want to say that this theorem is very useful for perturbation of FDEs or parabolic equations. You have to be a little, it's more difficult to use it for if you take, if you go outside the class of parabolic equations. But then you run into a lot of problems. So now we go to the density, which is the density of Cook-Casmel and Morse-Mel. And so the first result is for functional differential equations. And the genericity of hyperbolicity of equilibria has been proved by Oliva in 1969. So I recall, so I have to apologize to the audience. I always denote by x sub t because it's shorter. For me, it is dx by dt, but in the world of functional differential equation, x sub t is this x sub t of theta is x of t plus theta. So in this slide, and only in this slide, I take the notation xt with the sense of the people in functional differential equations. And so I wrote just an equation. And in 1977, John Mallet-Paré showed that the set of f such that all critical elements are hyperbolic is a generic set. He also had a short paper, I think in around 1975, where he said that Cook-Caswell was generic. So, but I also put this transparency to emphasize the very fundamental paper of Hale and Glynn in 1986 about heteroclinic orbits of retarded functional differential equations. So it's a very important paper because he speaks about shifted exponential dichotomies as a functional setting where you get also some kind of functional setting of transversality. I will speak more about the functional way to express transversality tomorrow. And okay, so this is related also to the facts that I showed you before. And but I encourage you to look at this paper. I learned a lot in this paper, and also other people used it in the introduction of the paper of Brunowski and Polacek. They also tell that this paper played an important role, I think. So now, let me go to the parabolic equation. So this is the first result is about automatic transversality. So you take a parabolic equation in one dimension. So omega is 0, 1, the interval 0, 1. I call it also y to show you, to indicate that it's an interval. And you look at the equation du by dt equal to uxx plus f which is a function of x, u, and ux. And here I take a favor, and my favor of, okay, you take what you want here, you take a good function space. And here, you see you are in one dimension, and you have a function depending on x, u, and ux. So in some sense, when you see the equation, you would, it's not obvious that it is a gradient system. But in 1968, Zeleniak showed that it's a gradient system, despite that you have the presence of an du by dx. And Brunowski and Shunichou in 1984, Smoller and Wasserman the same year, a little later, a few months later, and both papers were appeared in the GDE, showed that you have generic hyperbolicity of the equilibria. Okay, I cannot quote all the person who was working on generic hyperbolicity of the equilibria, maybe in some more complicated, for some more complicated operators than the Laplacian, and I just want to, because we are about generic hyperbolicity. And so anyway, so in 1985 there appeared this very important paper of Dan Henry, and later there was a paper of Engelland in 1986, where they showed that if E plus and E minus are two hyperbolic equilibria, then you have automatically the transversal intersection of the stable and unstable manifold. So if you put of course it implies, because you have a gradient system, that if you put a dissipation condition on F, then you can say SF of T is generically more small. So what is behind this result? Okay, so I must say the paper of Dan Henry is more general than the one of Engelland, because Dan Henry also shows transversality even of strongly stable and unstable manifold, even if you don't have hyperbolicity. And the paper of Dan Henry contains a lot of things about the study of asymptotics when t goes to plus infinity, when you go when you converge to an equilibrium point. And so what is behind, you will see in the dimension 1 case, it is because you have a very nice, property, which is the Sturm properties. So Bernard Fiedler calls it Sturm properties in his papers. So, but it's also called, so it tells Sturm number, but it's also called zero number and Lapp number. So here I take the zero number, which is the number of strict sign changes of a function phi in I. So if phi is in C1 of I to R, and which has zero boundary conditions. So this is goes back to Sturm in the regular case, and he says that if you have a linearized equation, so you again see the importance of linearized equations. So the number of zero of the function for t fixed is finite. It is non-increasing in time, and it strictly decreases at the time t0 if and only if you have a multiple zero. So when you apply it to the nonlinear case, of course you apply it or to the derivative du by dt, which is a solution of a linearized equation, or you apply it to the difference of two solutions. So if you want to, there is a nice, there was a conference in 2005 in Geneva about Sturm-Liouville, and it's a very interesting book of proceedings that you could. So now, oh no, I go in the other way. So let me also say that in this case, when you are in dimension 1, we just saw the autonomous case. Now you can go to the non-autonomous case. You add an t, and you assume that f of t xu is time periodic of period omega. And you look now at the Poincaré map, which it means you take PF, it's the map which associated to the initial data U0, the solution at the time omega, which is your period. And so there were some results of Chen and Matano in 1989 and Brunowski, Polacek, and Sanchete in 1992, who said that each bounded orbit of the iterates of PF converges to the fixed point of PF. It means through a periodic orbit. And so there is, again, a very important paper of Chen and Hale in 1992, which says that if you have two hyperbolic fixed points of this Poincaré map, then you have automatic transversality of the stable and unstable manifolds. So this is not surprising because you are still in one dimension. You can use the properties of the zero number. So, but for me it's a very important paper because in this paper there was done a lot of hard work, and there is a very useful appendix B, which is very long, and about the asymptotics of perturbed iteration. And this appendix generalizes the work of Dan Henry. So they did a lot of hard work in this paper. Also, there is a very important appendix about the stable and unstable manifolds, and center stable and center unstable manifolds, and their tangent spaces, which are very useful in the later work of Polacek, Brunowski, and myself. So now we have seen a lot of automatic, how much I have? 5 minutes only? Okay, so I have to hurry, but don't worry, I will continue tomorrow, so I don't need to say everything today. So now I go to generic transversality, because we saw some automatic transversality, and now I am pleased to speak about the paper of Brunowski and Polacek in 1997, where they showed, so you take this is a gradient scalar parabolic equation. You take a parabolic equation any dimension, and you take a function which depends only on x and the value of u. So in this case, it's clearly you have a Lyapunov functional, it's clearly gradient. And so you have to worry, okay, about the hyperbolicity of the equilibria and the transversality of the stable and unstable manifolds of the equilibria. And so what is behind is what I told before. You have a lot of things behind this result. By the way, you see, it's not true if you have no genericity if you want to perturb only with the function which depends on one u. So what is behind? Now I go quickly because tomorrow I will come back to the harder works. So tomorrow we will work harder. So what is behind is the functional characterization of transversality. So some ideas come from Hale and Bean. It's the Hale and Bean paper, and also before. So for this I also spoke about the Robin paper for the functional characterization of transversality. And then they reduce the genericity proof to a non-vanishing condition of an integral. And we will see that tomorrow. And at the end, they use a property of singular nodal sets of the parabolic equation. Now, let us go outside this class of parabolic equation, and we go to the damped wave equation. And morally, not only for Morse-Mel or Kuka-Mel, there is the asymptotic behavior of a damped wave equation and the asymptotic behavior of a parabolic equation look similar. So based on this moral belief, I told to Pavel Brunowski, one has to prove it for the damped wave equation. So it was a little hard to convince him that it was also working, but as he was convinced, he really worked on it. And we showed that you have also Kopka-Smell in the case of the dumped wave equation. I will come back tomorrow. And Romain Joly, my former student, generalized it to a very delicate case, even in one dimension, when gamma, the constant, is replaced by gamma of x, and gamma of x can vanish at some places. Okay, so tomorrow you will see what we cannot use. We can no longer use some of the same. So we use the same type of proof as Brunowski and Polacek, but we have also difficulties. We don't have the regularity in finite time. So it means that instead of using continuous exponential dichotomies, we have to use discrete exponential dichotomies. But this is a pleasure to use it because Dan Henry, in his paper in 1994 in the Resenhas, anyway said that the discrete exponential dichotomy are stronger, it's a stronger concept and should be used instead of continuous exponential dichotomy. And then we use piezo expansion. And I just put that because I wanted to say that Jacques and myself in 2003, we showed that, okay, you don't have regularity in finite time for a dumped wave equation, but you know, you can show that if the function f is an analytic function with respect to the second variable, then on the connecting orbit and on any compact invariant set, you know that the map T gives the SFT of U0, V0 is a real analytic map. So I have 1 minute or 5? Even 5? No. Okay. So now the only thing that I want to say is now in this panorama, it is if you go to the non-gradient case, you might think that everything is lost, but there is a miracle. So if you take the parabolic equation uxt equal to u, so there is a typing mistake. This is du by dt, I forgot to correct it, equal to uxx plus f of x ux. But now you look on S1, so it means with periodic boundary conditions. Then